All right, this is a beautiful number theory challenge. The challenge is to find for each positive integer n at least 1, find an n-digit number that is divisible by 2 power n and contains only the digits 2 and 3. So in this video, I'm going to give you a non-constructive proof. I'm going to always show that for every n there exists such an n-digit number, and we're going to actually walk through small values of n to get a feel for it. And I'm going to leave a challenge to you. Can you actually write down what that number should be, for example, in some cases? So let's just dive into the video, and what we're going to do is just look at what this looks like for n equals 1, 2, and 3. So for n equals 1, we're looking at a one-digit number divisible by 2 power 1, which is 2. Of course, 2 is the only number. It has to also contain only the digits 2 and 3. So 2 is the only number. When n is equal to 2, we're looking at a two-digit number that is divisible by 2 squared, which is 4, and contains only the digits 2 and 3. So again, it has to be even. It can't end in 3. The possible numbers are 22, 23, 32, and 33, but the one number that is divisible by 4, only one exists, and that is 32. Okay, that is divisible by 4 and only contains the digits 2 and 3. And we can keep going. Okay, so for n equals 3, they're going to be how many numbers? They're going to be 8 possible numbers, 2 cubed, because 3 digits, and each digit can be either 2 or 3. So 2 choices for each digit, 2 power 3 choices in total. And out of those, it turns out only 1 is divisible by 2 cubed, which is 8. And that number is actually 232. So as a challenge, I encourage you to try to find out what the number should be for 4 digits. Divisible by 2 power 4 is 16 and only containing 2 and 3. You might like to do that to get a feel for it, but 232 works because it's equal to 29 times 8, 2 cubed, right? 30 times 8 is 240. So you subtract 8 from that, you get 232. Now, how do I show that for every n there is such an n-digit number? I'm going to actually prove something a lot stronger. I'm going to show there's only one such number, and I'm actually going to show something even stronger than that, okay? So it's going to be very beautiful, but it's an example of a non-constructive proof. So we're going to have a lot of fun with this. Non-constructive means we're not even going to tell what the number is, but show it exists, okay? So don't forget to smash that like button and hit the subscribe button. I've got, 240 plus videos on my channel across all topics and levels. I'm building an elite library of mathematics. I'm a research mathematician. So by encouraging me, by liking and subscribing, it really encourages me to continue providing this free accessible content for everyone in the world to watch and enjoy. So what we're going to do is we're going to actually look at the following. We're going to prove the following statement. We're going to take an n, okay, a positive integer n, and we're actually going to look at the possible remainders when you divide n-digit numbers containing only 2s and 3s as digits by 2 power n. Okay, so first of all, if you look at n-digit numbers containing 2s and 3s, okay, n digits and contain only 2s and 3s. How many such numbers are there? So we've seen already that there are 2 power n such numbers because there are 2 choices for each digit and there are n digits in total, 2 times 2 times 2 up to 2 power n possible numbers. Okay, so there are 2 power n such numbers with this property, and we want to show at least one is divisible by 2 power n. Now what we're going to observe is that we're going to take remainders when you divide these numbers by 2 power n, okay? So what happens when you divide by 2 power n and look at the remainders, okay? Now, if you divide by 2 power n, a remainder could be any number. What is a remainder? Let's write it down. Remainder is going to possibly be 0, 1, 2, all the way up to 2 power n minus 1. Those are the possible remainders. There are 2 power n of them. We're actually going to prove that every remainder occurs exactly once when you're considering the 2 power n numbers that have n digits consisting only of the digits 2s and 3s. So we're going to show that every remainder occurs exactly once. In particular, the remainder 0 occurs, and that is a number that is divisible by 2 power n because we're dividing by 2 power n and contains only the digits 2s and 3s. Okay, so how are we going to do this? So let's just dive into that. I'm going to do it on this side of the board. So as an exercise, you can check, for example, n equals 2 when you're dividing by 4. Every remainder occurs once here. 22 is a remainder of 2 when you divide by 4, 23 is a remainder of 3 when you divide by 4, 32 is a remainder of 0 when you divide by 4, and 33 is a remainder of 1 when you divide by 4. So we're going to show this is true for every n, not just n equals 2. So let's look at 2 such numbers that contain only the digits 2s and 3s. Okay, so I'm just going to show you a brief decomposition just to give you a feel for it. If I write a number like 232, it is 2 times 10 squared, which is 200, 2 times 100, plus 3 times 10 power 1, plus 2 times 10 power 0. 10 power 0 is of course 1. Okay, so this is a way of writing it out as a decimal expansion. My point being that if I have an n-digit number that contains only the digits 2s and 3s, okay, you have one such n-digit number, you can write it as a summation Okay, some k varies from 0 to n minus 1. Okay, so 3-digit numbers, we got a highest power of 10, which was 2. That's n minus 1. N is the number of digits. So we get some k varies from 0 to n minus 1 of ak times 10 power k. This is the decimal expansion of our number, and we're given that, our numbers, we're considering all the digits are 2 or 3. So we write this mathematically as ak is in 2, 3 for all k. So I could write this for all k. And similarly, we're going to have another number. Okay, so we're going to look at another number that only contains of the digits 2s and 3s. Some k varies from 0 to n minus 1 of bk 10 power k, where again all the digits are just going to be 2s and 3s. And what I'm going to show is that these two numbers have different remainders when you divide by 2 power n. That means if they're distinct numbers, their remainders are going to be different when you divide by 2 power n. And that means that because they're 2 power n such numbers, all the remainders have to occur, each one exactly once. Okay? So how do I show that these two numbers have different remainders when I divide by 2 power n? Well, what I'm going to show is I'm going to show their difference is indivisible by 2 power n. Okay, so that's the same as saying they have different remainders. If their difference is indivisible by 2 power n, how am I going to show that? Let's get into that. So let's evaluate their difference. Okay, so their difference is going to be, if I actually take their difference, I'm going to get the following. I'm going to get some k varies from 0 to n minus 1, right? Some k varies from 0 to n minus 1 of ak minus bk times 10 to the k. That's going to be their difference. And now observe the following. Because ak is either 2 or 3 and bk is either 2 or 3 for each k, the possible differences ak minus bk are all going to be inside the set consisting of -1, 0, and 1, right? So if ak is 2, bk is 3, you get -1. If ak is 3, bk is 2, you get 1. And if ak and bk are equal, either both 2 or either both 3, you get 0. So this is going to be the expansion of the difference. We want to show this is not divisible by 2 power n, knowing that they are different numbers. So, at least one of these numbers is non-zero. Because, of course, if all of the numbers are 0 and they're the same number, the difference is 0, which is divisible by 2 power n. Okay? So aside from that, this is indivisible by 2 power n. Let's do that. All right, so because all these coefficients are -1, 0, or 1, we're just adding and subtracting powers of 10 up to 10 power n minus 1. Some powers of 10 may have a coefficient of 0. Okay? We don't know. But what we can say is that there's going to be a smallest power of 10 that has a non-zero coefficient. Because at least one power of 10 has a non-zero coefficient. Otherwise, this number is 0, and as I said, they're the same number. So the smallest power of 10, let's say 10 power I, that has a non-zero coefficient. Okay, so it's going to be either plus or minus 1. We don't know. So 10 power I, and all other lower powers of 10 have a coefficient of 0. So it's just going to be 0. Okay, just going to be adding a bunch of zeros. And the point is that you could potentially go up to other powers of 10. We don't know which powers of 10 occur, which coefficients are non-zero, but the highest possible power is going to be 10 power n minus 1, if it exists. Okay, the coefficient could either be 0, -1, or 1. But the idea here is that when we divide this whole thing by 2 power n, we want to show the remainder is non-zero. Okay, we want to show it's indivisible by 2 power n. Now, how do we do that? Well, if you divide by 2 power I plus 1, okay, let's just take I plus 1. Okay, I'm going to divide by 2 power I plus 1. Now, if I divide by 2 power I plus 1, then what happens is that all the higher powers of 10 are going to be divisible by 2 power I plus 1. All of these powers of 10 that occur later on are all going to be divisible by 2 power I plus 1 because it's 10 power I plus 1, 10 power I plus 2, etc. They're all going to be divisible by 2 power I plus 1. So when you divide this whole number by 2 power I plus 1, you're going to get the remainder of 0 here. But this number, its remainder is not going to be 0. 10 power I is indivisible by 2 power I plus 1, right? 10 power I is equal to 2 power I times 5 power I, that's its prime factorization, is not divisible by 2 power I plus 1. So therefore, the remainder when you divide this number by 2 power I plus 1 is non-zero, the whole number. And therefore, the remainder when you divide by 2 power n is also going to be non-zero because 2 power I plus 1 is a smaller power of 2 than 2 power n. Because I is less than or equal to n minus 1. So I plus 1 is less than or equal to n. So dividing this whole number by 2 power n will also have a non-zero remainder. Therefore, these two numbers, they are distinct numbers consisting only of 2s and 3s, n digits. Their difference is indivisible by 2 power n. So they have different remainders when you divide by 2 power n, which means every remainder, because they are 2 power n numbers consisting only of the digits 2s and 3s, are n-digit numbers. So every remainder from 0, 1 to up to 2 power n minus 1 occurs exactly once In particular, a remainder of 0 must occur exactly once, and that number is divisible by 2 power n. That is our n-digit number consisting only of the digits 2s and 3s. Hope you loved that video. It's a lot of fun, right? You can actually constructively give a proof as well. And what I want you to do is give me a 4-digit number, 5-digit number, 6-digit number, try to play around with it and find it consisting only of 2s and 3s and divisible by 2 power n. Can you do that? Drop a comment down below. I've got 2 fun videos for you now. You're going to love these videos. They're so exciting. The first video is going to be a proof that 1 factorial squared plus 2 factorial squared all the way up to n factorial squared for n greater than 1 is never a perfect square. Okay, it's going to use modular arithmetic, which we secretly used in this video too, but I try to do it without saying that. It's a lot of fun, and it's introduction to modular arithmetic ideas as well as non-modular arithmetic ideas to prove that statement. Check it out. It's going to pop on the screen. You'll love that video. It's so much fun. And another fun video you're going to love is the number 2 power 29 has 9 distinct digits. Okay, it's a 9-digit number. Each digit appears exactly once except 1. You've got 0, 1 through 9 are 10 possible digits. 1 digit is missing. Without calculating, find out that digit in this video. Genius trick. Have an amazing day.